You are moving at the speed of light, not metaphorically, not poetically. The speed of light is 300,000 kilometers per second. At that speed, you would circle the Earth 7.5 times in a single second. From the Sun to the Earth, 8 minutes. From the Sun to Pluto, about 5.5 hours. At that speed, you are moving across the universe, and you have been moving for 10 billion years. The light around you is not local. It is ancient. It left its sources when the universe was less than 4 billion years old. The galaxies you pass are not the galaxies of today. They are younger, smaller, brighter, more chaotic. Their stars burn blue and short-lived. Their black holes are still growing. Their collisions have not yet happened. And then the sky changes. Ahead of you, stretching across the visible sky, there is a concentration of gamma-ray bursts. 14 of them, clustered together at nearly the same distance, in nearly the same direction. They are not scattered. They are arranged. They form a wall 10 billion light-years long, 7.2 billion light-years wide, 1 billion light-years thick. The Hercules-Corona Borealis Great Wall, not a wall of stone, not a wall of matter in the ordinary sense, a wall of galaxies, quasars, and dark matter bound by gravity into a structure so vast that it occupies more than 10% of the diameter of the entire observable universe. This structure should not exist. There is a principle in cosmology called the cosmological principle. It is not a guess. It is not a preference. It is a foundational assumption. It states that on the largest scales, the universe is the same everywhere. Not identical, but homogeneous. No direction is special. No region is privileged. Structure exists at small scales, but above a certain size, the universe smooths out. The theoretical limit for structure size, under this principle, is approximately 1.2 billion light-years. The Hercules-Corona Borealis Great Wall is 8 times larger than that limit. If this structure is real, the cosmological principle is false. The universe is not the same everywhere at the largest scales. There are regions of the cosmos that are structurally distinct from others. The laws of physics do not forbid this, but the standard model of cosmology assumed it. The standard model of cosmology may have been wrong. This is what you are moving toward. Not a structure you can see, not a wall in the sense of an obstacle, a gravitational contradiction, written in gamma rays, stretching across the sky like a scar. It is the largest known structure in the observable universe, and it is what we are going to spend tonight with. Hello, and welcome to Sidereal. Tonight, we are going to sit with the largest objects ever measured. Not just big, the largest possible. Stars so immense they would swallow the orbit of Saturn. Black holes weighing tens of billions of suns, and the open question of which one weighs the most. A nebula that has produced some of the most massive stars ever confirmed, and a recent revision of just how massive those stars actually are. A void so empty that, had our galaxy formed inside it, we would not have known other galaxies existed until the middle of the 20th century. A galaxy so large that astronomers are still arguing about where it ends, and at the close, the structure that may or may not have broken cosmology, the one you just crossed. If this is your first night with us, consider subscribing, and if you're listening from somewhere quiet, leave your location and the time. We read everyone. Tonight's question is simple to ask and difficult to sit with. What does it mean to keep finding things that are larger than the rules say they should be? Let us begin where all stories of size begin, with the stars, the ones that contain everything we know about the word giant. Before the Great Wall, before superclusters, before even galaxies, there were the stars. And among stars, some are so large they break the human instinct for scale. We are not speaking of the Sunday. The sun is ordinary. It is a middle-aged star of average mass and average temperature. It is not the largest. It is not the smallest. It is not even close to either extreme. There are stars in this galaxy that dwarf the sun so completely that the sun becomes a speck of light at their feet. 3 of these stars are worth knowing, because together they tell the story of how badly we underestimate things we cannot fully resolve. The first is Uy-Scuti. It was first catalogued in 1860 by German astronomers at the Bonn Observatory. They gave it a routine designation in a survey of faint stars. They did not know what they had found. No one did. It was simply another point of light in a catalogue of thousands. They noted that it varied in brightness over a period of approximately 740 days. This made it a variable star interesting, but not remarkable. It was filed away. For nearly 150 years, that was all anyone knew about Uy-Scuti. In 2012, a team using the Very Large Telescope in the Atacama Desert of Chile turned their attention to it. The Very Large Telescope is not one telescope, it is 4 telescopes, each with a main mirror 8.2 meters across, capable of combining their light to achieve the resolution of a single mirror 16 meters wide. That is enough to measure the diameter of a star in another part of the galaxy directly, rather than inferring it from brightness and temperature. To do that, you need to resolve the star's disk to see it as more than a point of light. For most stars, this is impossible. They are too far away, too small, but a red supergiant's atmosphere is so extended that its edges become visible, if the instrument is precise enough. The Very Large Telescope measured Uy-Scuti's radius at approximately 1,708 times that of the Sun, with a margin of error of plus or minus 192 solar radii. That margin alone spans nearly 200 suns. Even at the lower bound, Uy-Scuti was enormous. Its diameter works out to approximately 2.376 billion kilometers. Its radius alone is almost 8 times the distance from the Sun to the Earth. Placed at the center of the solar system, its photosphere would extend past the orbit of Jupiter, and its thinning outer atmosphere would reach towards Saturn. The volume of Uy-Scuti is approximately 5 billion times the volume of the Sunday. 5 billion suns could fit inside a sphere the size of Uy-Scuti. The mass, however, is only 7 to 10 times the mass of the Sunday. This is why red supergiants are described as puffed up. They are not dense, they are enormous, but their matter is spread thin, a balloon of gas, not a lead ball of the same weight. Uy-Scuti is the balloon. But the title of largest known star did not stay with Uy-Scuti for long, and it did not leave quietly. In 2023, new measurements revised Uy-Scuti's radius down significantly to something closer to 900 solar radii. Still enormous. Still more than 900 times the Sun's radius, but less than half of what had been reported a decade earlier. The correction was not a mistake in the original sense. It was the inevitable result of trying to measure something without a fixed edge. Stars do not have solid surfaces. There is no boundary where the star ends and the vacuum begins. The photosphere is the layer from which most of a star's light escapes its apparent surface. Above that, the atmosphere continues to thin outward for millions of kilometers, fading gradually into the interstellar medium rather than stopping at a line. When astronomers measure the radius of a star like Uy-Scuti, they are measuring where it becomes opaque to its own light, not where it physically ends. Limb darkening complicates this further. The outer edge of a star's visible disk is dimmer and redder than the center, and different instruments, at different wavelengths, draw that boundary in slightly different places. This is why the same star can be reported at 1,700 solar radii in one decade and 900 in the next. The astronomers were not wrong. They were measuring a cloud, and clouds do not hold still. In the meantime, another star had already taken the crown and held it for longer. Stephenson 2-18 is named after its discoverer, Charles Bruce Stephenson, an American astronomer who in 1990 was cataloguing an open star cluster using deep infrared survey data. He was not hunting for the largest star in the universe. He was mapping a cluster of stars born from the same molecular cloud, in the constellation Scutum, the Shield. He named the cluster Stephenson 2. It contained 25 red supergiants. The brightest of them, listed simply as object number 18, would later be measured as the largest star known. Its radius is estimated at approximately 2,150 times that of the Sun, with an even larger margin of error than Uy-Scuti's. The diffuse edge problem is worse here, not better. Its diameter comes out to roughly 3 billion kilometers, close to the distance from the Sun to Uranus. Placed at the center of the solar system, its photosphere would extend past Saturn's orbit, and its outer envelope would reach toward Uranus. It would swallow Jupiter itself 1,000 times the volume of Earth without slowing down. The volume of Stephenson 2-18 is approximately 10 billion times the volume of the Sunday. Its surface temperature is approximately 3,200 Kelvin, considerably cooler than the Sun's roughly 5,778 Kelvin, which is why it burns red rather than yellow-white. Here is the fact that tends to stay with people. If you could take a commercial aircraft, not a rocket, an aircraft cruising at 900 kilometers per hour, and fly it around the circumference of Stephenson 2-18, the trip would take approximately 1,200 years, longer than the entire construction history of most of Europe's great cathedrals. You would be vaporized before completing the first kilometer. The thought experiment holds anyway, because the number is the point, not the survival. And yet the mass of Stephenson 2-18 is only about 18 times the mass of the Sunday. Like Huge-LQG, it is puffed up an enormous volume of space, holding very little actual matter. If you could somehow stand inside it, the gas would be so thin it would be nearly indistinguishable from the vacuum outside. These are not the only stars in this class, and that matters because a single extreme example can look like an anomaly. A second and third example start to look like a population. VY Canis Majoris, in the constellation Canis Major, is smaller than either Huge-LQG or Stephenson. 2-18, its radius is generally placed around 1,420 solar radii. But it is one of the most carefully studied red supergiants we have, precisely because it is close enough and bright enough to observe its mass loss directly. VY Canis Majoris is losing mass at a striking rate, shedding gas into space through stellar winds and outbursts that have built a vast, asymmetric nebula around the star itself, visible in its own right through a telescope. Astronomers studying it are not just measuring a star, they are watching a star disassemble itself in real time, decades before it dies. That mass loss is not incidental. It is the mechanism behind nearly everything we have just described. A star cannot keep growing indefinitely outward. At some point, the outer layers become only loosely bound to the core, held by a gravity weak enough that radiation pressure and stellar winds can simply carry pieces of the star away. Red supergiants lose material continuously throughout this phase of their lives, sometimes shedding gas equivalent to a meaningful fraction of a solar mass over a few thousand years. The star is not static. It is bleeding into space, even as we try to measure its edge. We have a closer example of this kind of instability, and a more recent one. Betelgeuse, in the shoulder of Orion, is a red supergiant roughly 640 light-years away, close enough to be one of the most watched stars in the sky, and bright enough to see without a telescope. In late 2019, Betelgeuse began to dim, not slightly. By early 2020, it had lost more than half its usual brightness, the most significant dimming recorded in over a century of observation. The dimming spread through the astronomical community quickly, and so did the question underneath it. Was this the visible beginning of a supernova? It was not. By 2021, researchers using the Hubble Space Telescope had pieced together a different explanation. Betelgeuse had ejected a large cloud of material from its surface, something closer to a stellar sneeze than a stellar death, and that cloud had cooled into dust as it moved away from the star, drifting into our line of sight and blocking a portion of its light. The star itself had not changed. A curtain had simply passed in front of it. This is the kind of moment the narrator profile of this channel calls a moment of realization in miniature. Astronomers watching real data shift in real time, building one explanation, discarding it, and building another, in public, while the star simply continued doing what red supergiants do. It is worth understanding, briefly, why a star becomes this large in the first place, because the mechanism is not obvious. A star like the Sun spends most of its life fusing hydrogen into helium in a stable core, with the outward push of that fusion balanced almost perfectly against the inward pull of its own gravity, a long, quiet equilibrium that can last for billions of years without much changing on the surface. That equilibrium ends once the hydrogen at the core runs out. The core contracts and heats further. Hydrogen fusion shifts to a thin shell surrounding the now inert core, and that shell burns hotter and more intensely than the core ever did. The extra energy has to go somewhere. It pushes outward into the star's outer layers, which are far less tightly bound to the center than the core itself, and those layers respond by expanding not by a little, but by a factor of hundreds. This is the mechanism behind every red giant and every red supergiant we know of. a star's outer envelope inflating in direct response to a hotter, smaller engine running underneath it. The star is not growing because it has gained mass. It is growing because its insides have rearranged themselves, and the outside has nowhere to go but outward. This is also why the largest stars by volume and the most massive stars by mass are, with only partial overlap, different populations entirely. Huge-LQG and Stephenson 2-18 are red supergiants, bloated, relatively low-mass stars in a late and unstable phase of their lives, sitting an estimated 9,500 light-years and roughly 19,000 light-years from Earth, respectively, both in the constellation Scutum, neither one ever likely to be visited by anything we build. The most massive stars known, by contrast the ones clustered inside the Tarantula Nebula, which we are about to reach, are young, blue, searingly hot, and comparatively compact, packing far more mass into far less volume. Size and mass, it turns out, measure almost opposite things. A star can dominate one category by losing the contest in the other. So now we must ask the harder question. If a star can hold this much volume while shedding mass the entire time, what happens when gravity stops losing the argument? What happens when a collapsing core wins completely, and nothing, not radiation pressure, not stellar wind, not the outward push of fusion is left to resist it? The death of a star like any of these will not be quiet. The core collapses. The outer layers are blown outward in a supernova bright enough to briefly outshine its entire host galaxy. What remains at the center depends on exactly how much mass that core retained. Below a certain threshold, it becomes a neutron star, an object we will return to later. Above it, nothing can stop the collapse, and the result is a black hole, tens of times the mass of the Sun, compressed into a few dozen kilometers. The star that produced it was 3 billion kilometers across. What remains is smaller than most cities. It is worth sitting, briefly, with how rare a measurement like Huge-LQG's or Stephenson 2-18's actually is, directly resolving a star's disk, rather than simply inferring its size from brightness and temperature, the way the vast majority of all stellar measurements are made, has only ever been possible for a small handful of exceptionally large, exceptionally nearby red supergiants. Almost every other star in this galaxy, and every star in every other galaxy, is measured indirectly, through models, through assumptions about how stars of a given temperature and luminosity ought to behave. The two stars that open tonight's story are not just the largest known, they are nearly the only ones large enough and close enough for an instrument like the Very Large Telescope to have actually looked at their edges directly rather than taking the rest of stellar astrophysics' word for it. That is the largest scale we know how to build, at the level of a single dying star. It is not, however, the largest object we know of, not by a margin that is even close. We said we would come back to the neutron star. Let us do that now, before we move on to something that leaves nothing behind at all. A neutron star is what remains when a massive star's core collapses, but not quite enough to overwhelm every force of resistance matter has left. It is, by a wide margin, the densest object we can observe directly without resorting to a black hole's mathematics instead of its physics. A typical neutron star is approximately 12 kilometers across, smaller than most cities, and contains roughly 1.5 times the mass of the Sun. Compress the Sun down to the size of a small city, and you have, very roughly, what a neutron star actually is. The density that implies is difficult to translate into anything a person can hold on to, but it is worth one attempt. A single sugar cube-sized piece of neutron star material, brought to Earth, would weigh roughly as much as a mountain, not metaphorically heavier, genuinely, if you could somehow keep it from immediately collapsing through the floor and through the planet beneath it. A sugar cube of this material would weigh something on the order of 1 billion tons. The matter is not exotic in composition. It is made of the same particles as everything else. Protons, neutrons, electrons, but gravity has packed it together so tightly that the electrons have been forced into the protons, converting nearly the entire star into a single, almost solid mass of neutrons, packed at nuclear density, the same density found inside an atomic nucleus, but spread across an object 12 kilometers wide instead of a few femtometers. These objects were not predicted into careful existence and then dutifully found. They were found first, and understood only after a young researcher refused to dismiss something that did not fit any known explanation. In 1967, Jocelyn Bell, then a graduate student at Cambridge University, was analysing data from a radio telescope array she had helped build in the English countryside, designed to study a completely different phenomenon. Buried in months of recorded data was a signal so regular, pulsing at a fixed interval, over and over, with a precision unlike anything natural that anyone on the team had previously encountered, that her supervisor's team briefly logged it under the half-joking designation LGM1, Little Green Men. No known natural process produced a signal this clean. For a short time, the possibility that they had detected an artificial transmission from an alien civilization was taken seriously enough to be discussed before anyone was prepared to say it aloud as a real conclusion. It was not a signal from anyone. It was a neutron star, spinning on its axis many times per second, sweeping a beam of radio emission across the sky, the way a lighthouse sweeps its beam across the sea, visible from Earth only on the moments that beam happened to point directly at us, and only because the star's rotation was, and is, almost unimaginably stable. Bell and her supervisor, Anthony Hewish, soon found several more of these signals, coming from different directions in the sky, each with its own distinct, regular period, ruling out a single coordinated transmission and confirming instead that they had found a previously unknown class of astronomical object. We now call these objects pulsars, and Bell's discovery remains one of the cleanest examples in the history of this science, of a researcher noticing something the instruments were not built to look for, and simply refusing to assume it had to be a mistake. Not every neutron star announces itself this clearly. Some, called magnetars, carry magnetic fields trillions of times, stronger than anything we can produce on Earth. Fields so intense that, at sufficiently close range, they would distort the electron orbitals of ordinary atoms before you got anywhere near the star itself. Others spin far faster than the pulsars Bell originally found. The fastest known rotate several hundred times every second, their surfaces moving at a meaningful fraction of the speed of light, even while the star as a whole sits still in space. The surface gravity of an ordinary neutron star is roughly 100 billion times stronger than the gravity holding you to the floor of whatever room you are listening in right now. Drop an object from a height of 1 meter above a neutron star's surface, and in the time it takes you to read this sentence, it would already have struck the surface at a meaningful fraction of the speed of light, assuming, of course, that the object, and the concept of dropping it, survived contact with that gravity at all, which it would not. And these stars are not perfectly smooth, unchanging spheres, despite their density. Pulsars occasionally undergo sudden, tiny changes in their rotation rate, called glitches, the crust of the star abruptly cracking or shifting, in events thought to resemble a kind of stellar earthquake, briefly speeding up the star's spin by an amount too small to notice without years of precise timing, and then settling back into its slow, gradual slowdown. Even an object this extreme, spinning with the precision of an atomic clock, is not perfectly still underneath. Something is still happening, even here. And in 2017, 2 neutron stars did something that connected this entire section directly to a structure we are going to spend real time with later tonight. 2 neutron stars, locked in a decaying orbit around each other for hundreds of millions of years, finally spiraled close enough to collide, an event detected first as a ripple in space-time itself, a gravitational wave, picked up by detectors on opposite sides of the United States, and then, a little over a second later, as a short gamma-ray burst, observed by satellites watching the same patch of sky. It was the first time a single cosmic event had been confirmed through both gravitational waves and light, and it directly confirmed what astronomers had long suspected, that neutron star mergers are one of the primary sources of short gamma-ray bursts, the very same category of flash that, scattered across billions of light-years and billions of years of cosmic history, will eventually help define the largest, most disputed structure of the entire night. There is a specific mass threshold separating these two outcomes, named after the people who worked out where it sits. Below roughly 1.5 to 2 times the mass of the Sun, packed into a core this dense, the quantum mechanical pressure of tightly packed neutrons is enough to halt the collapse and hold the star up against its own gravity indefinitely. This is essentially the same kind of pressure that, at a lower density, holds up a white dwarf, a limit first calculated for that case by Subrahmanyan Chandrasekhar in the 1930s, and extended to neutron stars somewhat later by Robert Oppenheimer, George Volkoff, and Richard Tolman. Above that threshold, even neutron pressure is not enough. There is no known force capable of stopping the collapse at any point after that, and the core continues falling inward, past the density of a neutron star, past the point where any known physics describes what the matter is even doing, until at least according to general relativity, it reaches a single point of infinite density. A black hole is not really a different kind of object from a neutron star. It is what happens when the same collapse simply does not find anything left to stop it. A star that ends its life as a neutron star is, in a sense, the fortunate outcome of stellar collapse, violent but survivable, in the sense that something solid and observable remains. The other outcome, when the collapsing core retains too much mass for even neutron pressure to hold it up, does not leave anything behind to observe at all. There is a black hole called TON 618. It is not a star and not an ordinary galaxy. It is a quasar, a black hole at the center of a distant galaxy, actively pulling in surrounding gas and dust. The accretion disk around it glows so brightly that it outshines its entire host galaxy. We cannot see the galaxy. We can only see the light of material falling toward the black hole's edge. The most widely cited estimate of its mass, derived in 2004 from the width of an emission line in its spectrum, places it at approximately 66 billion times the mass of the Sun. For comparison, the supermassive black hole at the center of our own galaxy, Sagittarius A star, is a little over 4 million solar masses. TON 618 outweighs it by roughly 15,000 times. The black hole at the center of the galaxy Messier 87, the first black hole ever directly imaged, in 2019, is about 6.5 billion solar masses. TON 618 would still outweigh that by a factor of 10. That 2019 image is worth a moment, because it is the closest astronomy has come to actually seeing one of these objects, rather than inferring it from the motion of gas around it. The Event Horizon Telescope is not a single instrument. It is a network of radio observatories spread across the planet, from Hawaii to Spain to Antarctica, linked together and timed with such precision that, working in concert, they function as a single telescope, roughly the size of the Earth itself. The only practical way to resolve something as small, relative to its distance, as a black hole's silhouette against the glowing gas surrounding it. The resulting image of Messier 87's black hole, released after years of data collection and analysis by a large international collaboration, showed exactly what general relativity had predicted decades earlier. A dark central shadow, ringed by the bright glow of superheated gas bending around it. In 2022, the same network produced a second image, this time of Sagittarius A star itself, considerably harder to capture clearly because gas around our own galaxy's black hole moves and changes shape over minutes rather than days. No comparable image of TON 618 exists, or is likely to exist soon. It sits roughly 10 billion light-years away, more than 1 million times farther than Messier 87, putting it well beyond what even an Earth-sized radio telescope can currently resolve. We should be honest about the uncertainty here, because the channel's whole relationship with these numbers depends on being honest about it. A more recent analysis, published in 2019 using revised methods, places TON 618's mass closer to 40.7 billion solar masses, a meaningfully smaller number than 66 billion, though still enormous by any standard. The two estimates differ because deriving a black hole's mass from the width of light emitted by gas swirling around it requires assumptions about the geometry of that gas, assumptions that are difficult to pin down for an object 18 billion light-years away. The lower estimate is now considered more likely by some astronomers. The higher one remains the figure most often quoted. Both numbers describe the same object. Neither is settled. What is not in dispute is the category. The term for objects at this scale is ultramassive black hole, distinct from the merely supermassive black holes, which top out in the low billions of solar masses that sit at the centers of most large galaxies, including our own. The event horizon of TON 618, the boundary beyond which nothing can escape, has a diameter of approximately 2,600 astronomical units. An astronomical unit is the distance from the Sun to the Earth, about 150 million kilometers. 2,600 of them is roughly 86 times the distance from the Sun to Neptune. It is a sphere of darkness, the size of a small planetary system, holding the mass of tens of billions of stars. In ordinary units, that event horizon is something like 400 billion kilometers across. The red supergiants we just spent an hour with were 3 billion kilometers across at most. The event horizon of this black hole is more than 100 times larger than the largest star we know, larger than the orbit of Neptune, larger than the photosphere of Scuti by an enormous margin. A black hole, despite being defined by the absence of light, is not necessarily small. This one is vast. How could something become this massive this quickly? TON 618's light left it when the universe was less than 4 billion years old. The standard models of black hole growth do not easily produce 66 billion or even 40 billion solar masses in that span of time. There are mechanisms that could explain it. Galaxy mergers that combine smaller black holes, the direct collapse of an enormous gas cloud into a black hole without ever forming a star first, and a process called super-Eddington accretion, in which a black hole pulls in matter faster than the standard physical limit on accretion would normally allow. That standard limit is worth explaining, because it is not arbitrary. As gas falls toward a black hole, it heats up and radiates light, the same accretion disk glow that let Marie-Helene Ulrich identify TON 618 as a quasar in the first place. That outgoing light exerts its own outward pressure on the infalling gas behind it, the way sunlight gently pushes against anything it strikes. Pull in matter quickly enough, and the radiation produced becomes intense enough to push new infalling gas away before it can fall any further, throttling the black hole's own growth. The Eddington limit is the point at which that outward push and the inward pull of gravity reach a balance, a natural speed limit on how fast any black hole, in principle, ought to be able to grow. Super-Eddington accretion describes circumstances in which a black hole appears to exceed that limit anyway, usually because the infalling gas is unevenly distributed, allowing some of it to slip past the radiation pressure through gaps the light cannot effectively reach. It is not a violation of physics. It is a loophole physics seems to permit under the right, narrow conditions. Conditions TON 618 would have needed to satisfy almost continuously for hundreds of millions of years to reach the mass we measure today. None of these mechanisms, on their own, comfortably explains an object this large, this early. It remains a genuine, unresolved problem, not a mystery in the dramatic sense, but a real gap between what our models predict and what we have actually measured. There is a theoretical ceiling here worth knowing about. In 2015, the astrophysicist Andrew King calculated that a non-rotating black hole growing purely through accretion should top out somewhere around 50 billion solar masses, a limit set by a quirk of gravity near the black hole's innermost stable orbit. A rapidly spinning black hole could push that ceiling much higher, potentially as far as 270 billion solar masses. TON 618, at either of its quoted masses, sits close to or above the non-spinning limit. If the higher estimate is correct, this may be one of the most massive black holes that physics, as we currently understand it, permits to exist at all, and it may not even hold the record much longer, or may have already lost it. Observations of the Phoenix galaxy cluster have suggested its central black hole could weigh as much as 100 billion solar masses, a number derived differently through the dynamics of the surrounding cluster rather than emission line width, and one that comes with its own substantial uncertainty. The largest black hole we know of is, right now, a moving target. That is not a flaw in the science. It is what science looks like while it is still in progress. But we have moved ahead of the discovery itself. Let us return to it. TON 618 was first catalogued in 1957 by the astronomers Braulio Iriarte and Enrique Chavira, working at the Tonantzintla Observatory in Mexico. They were surveying faint blue stars, objects that appear blue because they are hot, the way a flame is blue at its hottest point. TON 618 appeared blue in their photographic plates. They listed it, catalogued it under the observatory's own numbering system, and moved on. Nothing about it stood out yet. Quasars themselves would not even be recognized as a distinct category of object for another 6 years. In 1963, the astronomer Martin Schmidt, working at the Palomar Observatory, took a spectrum of an object catalogued simply as 3C273, a point of light that had been assumed, like TON 618 would later be assumed, to be an unusually bright star. Schmidt found emission lines he could not immediately identify until he realized they were ordinary hydrogen lines, shifted dramatically toward longer wavelengths by the expansion of the universe itself. The shift implied the object was billions of light-years away. At that distance, for it to appear as bright as it did from Earth, it had to be radiating more energy than an entire galaxy of ordinary stars from a region of space barely larger than our solar system. Nothing in the astronomy of the time offered an easy explanation for that combination of distance, brightness, and compactness. Schmidt's identification of 3C273 is generally treated as the moment quasars became a recognized category of object, rather than a handful of unexplained oddities scattered through earlier star catalogues. TON 618 would turn out to be one of the most extreme examples of exactly the same phenomenon, discovered 6 years before anyone had the framework to recognize it as one. In 1970, a radio survey conducted at the Institute of Radio Astronomy in Bologna, Italy, detected strong radio emission coming from the direction of TON 618. Ordinary blue stars do not emit strong radio signals, quasars do. This was the first hint that the object catalogued 13 years earlier was not a star at all. In the early 1970s, the astronomer Marie-Helene Ulrich, working at the McDonald Observatory in Texas, took optical spectra of TON 618. A spectrum spreads an object's light out by wavelength, revealing its chemical composition, temperature, and motion. What Ulrich found were broad, bright emission lines, not the narrower absorption lines you would expect from an ordinary star, but the signature of hot, fast-moving gas falling into something with overwhelming gravity. She was looking at the spectrum of an accretion disk. She recognized what that meant. This was the moment TON 618 stopped being a blue star and became a black hole. At least in our understanding of it, nothing about the object itself changed in that instant, only what we knew it to be. The mass itself would not be measured for years after that, and the method is worth understanding because it is the same method used for nearly every distant black hole we have discussed tonight. You measure how broad the emission lines are. Broader lines mean the gas producing them is moving faster. Faster motion, at a known distance from the center, means stronger gravity is required to hold that gas in orbit. From velocity and distance, you derive mass, the same logic Newton used to weigh the sun from the orbital speed of the planets, applied here to ionized gas orbiting something we cannot see directly at all. There is a real asymmetry between the black hole and the star we left behind in the last section. A star is a source it manufactures its own light through fusion, and that light pushes outward against gravity, holding the star's bulk in a kind of stalemate. A black hole is a sink. Nothing it contains generates light of its own. Whatever light we see from one comes entirely from matter that has not yet crossed the horizon, gas still falling, still glowing, still, technically, ours to observe. Past that boundary there is nothing left to measure. The density of TON 618, averaged across the volume enclosed by its event horizon, is in fact lower than the density of water, an entire small planetary system's worth of space, almost empty, wrapped around a single point where the equations stop behaving like equations at all. And despite all of that, the black hole was, in some sense, once a star or many of them. Every black hole of this scale begins as ordinary matter, hydrogen and helium, fused into heavier elements inside stars, scattered by supernovae, gathered again by gravity into the next generation, falling slowly inward over hundreds of millions of years until enough of it crosses a threshold and a black hole begins to grow at the center of it. TON 618's 66 billion or 40 billion solar masses did not arrive all at once. They were assembled, star by star, gas cloud by gas cloud, across the early universe, by a process we still cannot fully account for. The brightness produced by all of that infalling matter is, on its own, almost as difficult to hold in mind as the mass behind it. TON 618's total radiative output has been estimated at somewhere around 140 trillion times the luminosity of the Sun, bright enough that, despite sitting roughly 10 billion light-years away, it remains detectable at all, let alone bright enough for astronomers in 1957 to mistake it for a comparatively nearby star. None of that energy will last indefinitely. Quasars like this one are powered by a steady supply of infalling gas, and that supply is not infinite. As the surrounding material is consumed, or stripped away, or simply runs out, the accretion slows, the disk dims, and the quasar fades into something closer to the quiet, dormant black holes we see at the center of nearby galaxies today, Sagittarius A star included, which shows no sign now of the kind of violent feeding that once may have lit up galaxies like TON 618's host in the early universe. The black hole itself does not go anywhere. It simply stops being loud. The black hole remains, in the most precise sense, unexplained. Not a mystery to be solved by next year's headline. A gap between the model and the measurement, sitting quietly at the center of a galaxy we cannot even see. We must leave the black hole for a while and ask a different question. Where do stars like the ones we started with actually come from? Not the black hole, not the long-dead core, the beginning, the nursery itself. That beginning is a place, not an object. The Tarantula Nebula, also known as 30 Doradus, the largest and most prolific star-forming region in the entire local group of galaxies. The local group contains more than 80 galaxies: the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and a long tail of smaller dwarf galaxies around the edges. The Tarantula Nebula is not in the Milky Way. It sits inside the Large Magellanic Cloud, a satellite galaxy of our own, approximately 161,000 light-years away, close, by extragalactic standards, close enough to resolve individual stars within it. It was first observed in the 1750s by Nicolas Louis de Lacaille, a French astronomer who had travelled to the Cape of Good Hope in southern Africa to map the southern sky, which was still largely uncharted by European observers. On the 5th of December, 1751, he pointed a modest telescope at a patch of sky in the constellation Dorado and recorded a faint cloud of light, a nebula, he wrote, not accompanied by any visible star. He had no way of knowing what it was. He catalogued it and moved on. A century and a half later, the German astronomer Johann Bode included it in his star atlas Uranographia, published in 1801, designating it the 30th object in Dorado. The name 30 Doradus stuck for 2 centuries. The nickname Tarantula came later, born from photographs that showed long, curved filaments radiating from a bright central body, a spider spinning stars, rather than catching them. What happens inside this nebula is the most intense star formation anywhere nearby. It is a cloud of hydrogen gas, spanning hundreds of light-years, dense enough in places that gravity has begun pulling clumps of it into collapse. Those collapsing clumps are stars in the process of being born. At the heart of the nebula sits a cluster called R136, a dense knot of perhaps 200,000 stars packed into a volume small compared to the nebula surrounding it. For decades after its discovery, astronomers assumed the brightest point at the center of this cluster was a single, almost impossibly massive star. Some early estimates, before the 1980s, suggested it might weigh as much as 1,000 times the mass of the Sun, a number that, if true, would have broken existing theory about how large a single star could ever become. It was not one star. As telescopes improved, high-resolution imaging resolved the single point of light into dozens of separate stars, packed so tightly together that earlier instruments simply could not tell them apart. The 1,000 solar mass monster did not exist. What existed instead was something almost as strange, a genuine population of individual stars, each one independently among the most massive ever confirmed. The brightest of these is named R136A1, usually shortened to R136A1. It is, by current measurements, the most massive star known anywhere in the observable universe, and its measured mass has moved almost every time anyone has looked at it more closely. Early spectroscopic estimates placed its current mass somewhere between 250 and 320 times that of the Sunday. In 2022, Astronomers using the Gemini South Telescope's speckle imaging instrument obtained the sharpest image of the star to date, and the new data pointed to something smaller, somewhere between 170 and 230 solar masses. Even at that lower figure, it remained the most massive star known. The record simply moved, it did not change hands. The most recent modeling, published in 2025 using a new method for simulating the star's outer atmosphere, settled on a current mass of roughly 230 solar masses, with an estimated initial mass before decades of fierce stellar wind-stripped material away of around 346 solar masses. That detail matters as much as the number itself. R136A1 is not simply massive. It is actively losing mass, continuously, the way Betelgeuse and VY Canis Majoris were losing mass in the previous section, except violently faster, driven by radiation pressure so intense that it tears gas directly off the star's surface and flings it outward as a powerful stellar wind. The star we measure today is already smaller than the star that existed 1,000,000 years ago. When it formed, it will be smaller still in another 1,000,000 years, if it survives that long. It is not alone up there. Two close companions, named R136A2 and R136A3, sit nearby with estimated initial masses exceeding 500 solar masses each, and a separate runaway star called VFTS 682, ejected from the cluster entirely, carries a similar pedigree. Not far from R136 sits another extreme system entirely, Melnick 34, the most massive binary star system known. Two stars locked in mutual orbit with a combined mass exceeding 280 solar masses between them, each one individually massive enough to qualify for this same list on its own. A small number of stars in this single nebula account for a disproportionate share of all the ultraviolet radiation and stellar wind shaping the gas around them. Most of the energy lighting up the Tarantula Nebula comes from perhaps a few dozen of these stars, out of the hundreds of thousands forming there. Before any of these individual stars had been resolved, astronomers cataloguing the region in the 1960s simply listed R136 as a single unusually bright object, without any way to know it was several dozen extreme stars standing close enough together to look, from 160,000 light-years away, like one. Untangling that single point of light into its actual population took decades of improving resolution, first speckle interferometry, then adaptive optics, then space-based imaging, each technique peeling back another layer of stars that the previous one had blurred together. The history of this single cluster is, in miniature, the history of the entire largest known star problem we opened this section with. Every claimed record, at this level of distance and density, is provisional until the instrument improves enough to check it again. It is worth knowing what a pair instability supernova actually is, because it is one of the stranger ways a star can die, and it is the specific fate in an extremely massive star's core. Temperatures can climb so high that gamma rays themselves begin spontaneously converting into pairs of electrons and their antimatter counterparts, positrons. That conversion removes some of the outward radiation pressure that had been holding the core up against its own gravity, and the core responds by suddenly contracting. The contraction triggers a runaway burst of further fusion, releasing enough energy in moments to blow the entire star apart, with no core left behind at all, no neutron star, no black hole, nothing but expanding debris. It is a theoretically predicted, but only rarely confirmed, way for a star to die completely, leaving no remnant whatsoever. For a star like R136, a one to have avoided this fate, despite sitting well above the mass range where the instability becomes theoretically possible, it has to be losing mass through its stellar wind fast enough, for long enough, to drop below the threshold before its core ever reaches the critical temperature. The 2025 modeling suggests that is exactly what is happening. The star's own violent shedding of material may be quietly saving it from the most violent possible ending available to something it's size. What happens to stars this massive when they finally die is itself an open question, and a recent one. A 2025 study led by researchers at the University of Amsterdam modeled the likely evolutionary path of R136A1 and its two companions, and concluded that, despite their extraordinary mass, none of them are likely to end as a pair instability supernova and none of them are expected to produce a gamma-ray burst, the kind of event we will return to near the end of tonight's story, when we reach the structure that may or may not be the largest thing in the universe. Their fate, instead, appears to be a more conventional collapse into a black hole, after shedding enough mass through stellar winds that their final core falls within a more ordinary range. Even the most extreme stars we know, it turns out, may end in comparatively unremarkable ways. The James Webb Space Telescope turned its infrared instruments toward the Tarantula Nebula in 2022, and the images it returned showed something earlier telescopes could not. Thousands of newly forming stars still wrapped in the dust and gas that built them, including young protostars, still actively pulling in material from surrounding disks, stars in the act of becoming stars, rather than stars already finished. Webb's infrared vision sees through the dust that blocks visible light entirely, revealing structure that had simply been invisible before. There is a question underneath all of this that the theoretical mass limit for stars still has not fully answered. Models have long suggested an upper boundary somewhere around 150 solar masses, set by the point at which radiation pressure should blow away any additional infalling gas before a star can grow larger. The Tarantula Nebula's brightest stars sit well above that boundary. The limit has not been disproven exactly. It has been pushed, repeatedly, by stars that were apparently never told where it was supposed to be. There is a quiet side to all of this violence, and it is worth sitting with for a moment before we move on. The stellar winds tearing material off these stars travel at thousands of kilometers per second. The shocks they generate heat surrounding gas to millions of degrees. By any human measure, this is an extraordinarily violent environment. But the nebula spans hundreds of light years, and these processes unfold over hundreds of thousands of years. Scaled down to something a human nervous system could actually witness, none of it would look fast at all. It would look like stillness light without motion, gas suspended rather than streaming, change happening too slowly for the eye to register as change. Violence, at sufficient scale, becomes indistinguishable from calm. The stars born here will not live. A star of 100 solar masses burns through its fuel in only a few million years, a passing moment, set against the sun's expected 10 billion-year lifespan before ending as a supernova or settling into a black hole, recycling its material back into the gas around it, available to build the next generation. The Tarantula Nebula has likely been doing this for around 10 million years already, and will likely continue for millions more. Most stars in the universe are not born this way. Most form in smaller, quieter clouds, far from anything resembling this density of mass and radiation. The Tarantula Nebula is the exception, and exceptions are exactly where the most massive examples of anything tend to live. The Large Magellanic Cloud, the galaxy that holds the Tarantula Nebula, gave astronomers a different kind of lesson in 1987, not from inside the nebula itself, but from a massive star elsewhere in the same galaxy, close enough to be observed in a way no supernova had been observed before, or has been observed quite the same way since. On the 23rd of February that year, 3 separate underground neutrino detectors, one in Japan, one in the United States, one in the Soviet Union, none of them built to watch for anything like this, each recorded a brief, simultaneous burst of neutrinos, ghostly particles that interact with ordinary matter so rarely that trillions of them pass through your body every second without a single one of them striking anything. Hours later, astronomers on the ground saw a new point of light appear in the sky, in the same direction the neutrinos had come from. A star in the Large Magellanic Cloud had ended its life as a supernova, and its core collapse had released a burst of neutrinos that escaped the dying star and crossed 160,000 light-years of space, hours before the light from the explosion itself managed to fight its way out through the star's own collapsing layers. It was the first time anyone had directly detected neutrinos from a supernova, and it confirmed, almost exactly, what theoretical models of core collapse had predicted for decades without any way to test it. 3 detectors, on 3 continents, built for entirely different experiments, had each happened to catch the same handful of ghost particles arriving from the same dying star in the same few seconds, and none of the teams running them knew what they had until they compared notes afterward. The Tarantula Nebula and the star that became this supernova are not the same object. and are not even especially close to each other within the Large Magellanic Cloud, but they share an address, a satellite galaxy of our own that has, twice now, given astronomers something they could not have gotten anywhere else: a nursery building the most massive stars we know of, and a death close enough to confirm, for the first time, what happens in the instant one of them finally collapses. We are leaving the nursery now, and moving towards something with no stars in it at all. There is a void in the constellation Boötes. It is not the only void known, and it is not the largest, but it was the first one ever discovered, and it remains one of the most striking, because of just how empty it turned out to be. It is a region of space approximately 330 million light-years across. To put that in perspective, the distance from the Milky Way to the Andromeda Galaxy is approximately 2.5 million light-years. The distance to the nearest major galaxy cluster, the Virgo cluster, is about 54 million light-years. The Boötes Void is 6 times the distance to the Virgo cluster, and more than 100 times the distance to Andromeda, a spherical region where galaxies are, by comparison to everywhere around it, almost entirely absent. The void contains approximately 60 known galaxies. For a region of that volume, the expected number, based on the average density of the universe, is closer to 2,000. The void holds fewer than 3% of what we would otherwise expect to find there. The discovery happened in 1981. Robert Kirshner, then at the University of Michigan, was leading a survey of galactic redshifts alongside Augustus Oehmler, Paul Schechter, and Stephen Schechtman, mapping the large-scale structure of the universe along narrow lines of sight, the way you might survey a forest by walking a single path through it rather than mapping every tree. A redshift tells you how fast a galaxy is moving away from you, and from that, by Hubble's law, roughly how far away it is. Measure the redshifts of enough galaxies along one direction, and you can build a rough three-dimensional map of what lies along that line. In the direction of Boötes, the team found galaxies, then nothing, then galaxies again. A gap. They published the first description of it in 1981, and it was met immediately with skepticism. Some astronomers suspected a selection effect, a flaw in the survey, rather than a real feature of the universe. Kirshner's team kept measuring. They added more galaxies, more redshifts, more lines of sight. The gap remained. In 1989, Kirshner and his colleague Ron Marsky confirmed 15 scattered galaxies sitting inside the void, isolated points of light, not clustered, not connected, simply present in the emptiness. By 1997, the count had grown to 60, the figure still cited today. Here is what the void actually means, translated into something closer to a felt experience than a number. If the Milky Way sat at the center of the Boötes Void instead of where it actually is, we would not have known that other galaxies existed until sometime in the 1960s. This is not speculation about hypothetical physics. It is a direct statement about the limits of observation. We have close neighbors, Andromeda, Triangulum, the Magellanic Clouds bright enough to be seen without a telescope at all. A galaxy sitting at the center of the Boötes Void has no such neighbors. The nearest other galaxy would be so distant that no instrument built before the middle of the 20th century could have detected it. Edwin Hubble's measurements of Andromeda's distance in the 1920s would not have been possible from there. There would have been nothing nearby bright enough to measure. It would have taken the large optical and radio telescopes of the 1960s, and the systematic sky surveys that came with them, before anyone living at the center of that void could have looked up and confirmed they were not, in fact, alone in the universe. Hold that for a moment before we move on. You are standing, for the sake of this thought, at the center of the Boötes Void. There is nothing here to orient you, no bright neighbor hanging in the sky to tell you where the rest of the universe begins. The stars of your own galaxy still wheel overhead gravity, does not care whether you are isolated, but everything beyond them is simply dark, not because nothing is there, but because nothing is close enough to see. Your own galaxy's structure would look entirely ordinary from in here. Star clusters would still form. Supernovae would still light up the night sky on schedule. Nothing about living inside this particular galaxy would feel incomplete. The emptiness is a property of everything outside it, and from the inside, outside is simply not visible. For all of human history up to a few generations ago, every civilization that ever lived here would have looked at this sky and reasonably concluded that the universe ended at the edge of its own galaxy. They would have been wrong, but they would have had no way of knowing they were wrong. The void does not announce itself from the inside. It only becomes visible from somewhere else, looking in. The 60 or so galaxies that do exist inside the Boötes Void are not ordinary galaxies that simply ended up in an unusual location. Galaxies that live inside voids, studied across many different voids rather than just this one, tend to differ systematically from galaxies living in denser environments. They are typically smaller, bluer, and richer in gas, with star formation continuing later into their lives, a pattern most astronomers attribute to isolation itself. A galaxy embedded in a dense cluster is regularly disturbed. Tidal interactions with neighbors, mergers, gas stripped away by collisions, all of which tend to use up a galaxy's star-forming material relatively quickly and shut down its growth early. A galaxy sitting nearly alone inside a void has none of that. Nothing comes close enough to disturb it, strip it, or speed up its evolution. It is left, in effect, to develop slowly and quietly, on its own schedule, largely undisturbed by the kind of gravitational chaos that shapes galaxies almost everywhere else in the universe. The handful of galaxies inside Boötes are not failed examples of normal galaxies. They are closer to a controlled experiment in what a galaxy looks like when nothing ever interferes with it. Voids this size form through gravitational instability, acting on tiny initial fluctuations. The early universe was nearly uniform, but not perfectly so. Tiny fluctuations in density existed from the very beginning. Gravity amplifies those fluctuations over time. Denser regions pull in more matter and become denser still. Less dense regions lose matter to their denser neighbors and become emptier still. Picture a foam of soap bubbles. Each bubble is a void, and matter accumulates along the thin walls between them. Over billions of years, smaller bubbles merge into larger ones, and the walls between them thin out further. The Boötes Void is thought to be the product of exactly this kind of merger, several smaller voids that combined into one large one, with the handful of galaxies inside it simply having been caught in the expanding bubble before they could escape to a denser wall. This is a completely ordinary outcome under the standard cosmological model called lambda cold dark matter, or lambda CDM, a description of the universe as a mixture of ordinary matter, an invisible form of matter we will spend real time with before the night is over, and a form of energy driving the universe's expansion. Voids are an expected consequence of this model. They occupy most of the universe's volume. Galaxies, despite filling our imagination of what the cosmos looks like, are the rare exception. Emptiness is the default. Boötes, for all its fame as the first void ever discovered, is also no longer the largest one known, and it was overtaken fairly quickly, once astronomers started deliberately searching for more of them. Surveys conducted in the decades since 1981 have identified other voids of comparable or greater scale across different parts of the sky, including a void in the direction of the constellation Canes Venatici, estimated at well over 1 billion light-years across, considerably larger than Boötes, despite receiving a small fraction of its public attention. This is a pattern worth noticing by now, because it has repeated at almost every scale tonight. The first confirmed example of something draws the headlines, and the larger examples that turn up afterward, once people know to look for them, rarely generate the same attention the original discovery did. Boötes remains historically significant. It has not been the literal record holder for a long time. There is a stranger possibility worth mentioning here, one that is still being actively argued over. Since 2013, several independent surveys, counting galaxies across different parts of the sky at near-infrared wavelengths, have reported that the region surrounding our own local group appears to be significantly underdense compared to the universe at large, out to a distance of several 100 million light-years. Astronomers have taken to calling this the KBC void, after the surnames of the researchers who first reported it, or simply the local hole. Some estimates place its scale at several hundred megaparsecs across, large enough that, if real, it could be distorting our local measurement of how fast the universe is expanding, conveniently lining up with a long-standing discrepancy in cosmology known as the Hubble tension, where two different methods of measuring the universe's expansion rate keep stubbornly disagreeing with each other by an amount too large to easily dismiss as measurement error. Researchers studying the proposal have suggested that a galaxy sitting inside an underdensity would experience a kind of gravitational hill, with everything nearby gently sliding outward toward denser surroundings, motion that, measured from inside the void, would look indistinguishable from the universe, simply expanding faster than it actually is everywhere else. Other researchers remain unconvinced that the underdensity is as deep or as real as claimed, arguing it could be an artifact of how the surveys were conducted, or too shallow to meaningfully affect the expansion measurement either way. If the Milky Way genuinely does sit inside a void of its own, then everything we said earlier about Boötes, about a civilization forming inside an underdensity and having no way to know the rest of the universe existed, would not be a thought experiment confined to a distant constellation. It would be, at least partially, our own situation debated in real journals, right now. The discovery itself was not a single triumphant moment. It was Kirshner's team, adding redshifts one at a time, watching a gap persist that should not have persisted, checking for errors, finding none, and slowly becoming confident enough to publish something that other astronomers would immediately try to disprove. The controversy lasted for years before independent surveys confirmed the void was real. That is what discovery actually looks like in this field, less a flash of insight, more a gap that simply refuses to fill in no matter how many times you check it. We have spent 4 sections building upward: a single star, a single black hole, a single nursery of stars, and now a single void large enough to swallow all 3 with room left over. The question that has been sitting underneath all of it is simple. If the universe contains gaps this large, what is actually holding the rest of it together? The answer is gravity, operating at a scale most of us never have reason to think about. The structures bordering a void, its filaments, its walls, the clusters of galaxies along its edges, pull on each other across hundreds of millions of light years. The void itself is not a hole in the gravitational field. It is simply a region where that field is weaker, surrounded by regions where it is strong enough to organize everything nearby into structure. Galaxies are not scattered randomly through space. They flow along filaments, the way water finds the lowest path through terrain, gathering at the nodes where multiple filaments meet. We are about to follow one of those nodes home. The largest single galaxy by stellar extent in the observable universe is called IC 1101. The letters IC stand for Index Catalog. It was logged in the late 19th century as object number 1101 in that catalogue, an administrative number, nothing more, attached to something that turned out to be anything but ordinary. It was discovered on the 19th of June, 1790, by William Herschel, a German-born British astronomer, builder of his own telescopes, discoverer of the planet Uranus, and cataloguer of thousands of nebulae, whose true nature he had no way of identifying. The concept of a galaxy as a separate island of stars, distinct from our own, was still more than a century away from being established. Herschel pointed his telescope toward the constellation Virgo that night, recorded a faint patch of light, described it as a nebula, and moved on. It would not be properly understood or properly measured until the 20th century was most of the way through. Astronomers classify IC 1101 as a supergiant diffuse galaxy in technical papers. The category is usually abbreviated to 2 letters, a lowercase one standing for supergiant and a capital one standing for diffuse. Galaxies in this category are the largest known, found almost exclusively at the centers of rich galaxy clusters, where they have grown by slowly absorbing their smaller neighbors. IC 1101 sits at the center of exactly such a cluster, Abell 2029, approximately 1.04 billion light-years away, containing hundreds of galaxies bound together by gravity, with IC 1101 as the brightest and most massive among them. Most of the mass in a cluster like Abell 2029 is not actually in its galaxies at all. It is in a vast reservoir of superheated gas filling the space between them, heated to tens of millions of degrees by the cluster's own gravity, and detectable only in X-rays invisible to ordinary telescopes, but bright enough in this part of the spectrum to outweigh, by a considerable margin, every star in every galaxy the cluster contains. IC 1101 sits at the bottom of this enormous, mostly invisible reservoir of hot gas, embedded in the deepest part of the cluster's gravitational well, in exactly the position you would expect to find the single largest galaxy a cluster has managed to build, given enough time for everything around it to settle inward. Its diameter is genuinely disputed, and the dispute is instructive. Some estimates place it at approximately 5.6 to 6 million light-years across. When measured to include its full diffuse outer halo, the faint, extended envelope of stars stripped from smaller galaxies it has absorbed over billions of years. More recent measurements, using a stricter definition based on a fixed brightness threshold rather than the total extent of detectable light, suggest something closer to 400,000 light-years. Both numbers describe the same object. They are simply answering different questions. How far does the bright core extend, against how far does any of its light extend at all? The Milky Way, by comparison, is approximately 100,000 light-years across. Even by the more conservative measurement, IC 1101 is roughly 4 times our galaxy's size. By the larger measurement, it is 40 to 60 times larger. The galaxy contains approximately 100 trillion stars, more than 1,000 times the number in the Milky Way. Its core alone, with a radius of around 13,700 light-years, is larger than our entire galaxy. The stars packed into that core are old, red and yellow, not blue. There is no gas left to form new ones. Star formation in IC 1101 stopped long ago, and it is not going to start again. This is what astronomers mean when they call a galaxy a fossil, not a metaphor for old age in general, but a specific description. A galaxy that has exhausted the raw material needed to build anything new, and is left simply burning through what it already has, slowly, for billions of years, with nothing left to replace it. That slow burning has a genuinely long timeline ahead of it. The 100 trillion stars inside IC 1101 are not uniform in lifespan. The handful of more massive ones remaining will exhaust themselves in a few more billion years, exactly the way the most massive stars in tonight's earlier sections do. But the overwhelming majority of any old galaxy's stellar population, by sheer numbers, is made up of small, dim red dwarf stars that burn their hydrogen so slowly and so efficiently that the oldest ones in the universe have not yet had time to leave the stage at all, even after 13 billion years. Models suggest individual red dwarfs can continue burning for trillions of years, far longer than the universe has so far existed. A fossil galaxy like IC 1101 is not approaching darkness on any timescale a human institution will ever track. It is simply trading its brightest, fastest burning stars for its dimmest, slowest ones, over and over, for a length of time that makes billions of years feel like the short version of the story rather than the long one. It got this large through a process with a deliberately blunt name: galactic cannibalism. A smaller galaxy, drawn by gravity toward the center of its cluster, spirals slowly inward over hundreds of millions of years. It does not collide with the central galaxy. In any violent sense, galaxies are mostly empty space. After all, it merges. Its stars are gradually stripped away and absorbed into the halo of the larger galaxy. Its dark matter and any central black hole merge as well. IC 1101 is the accumulated result of this process repeated across cosmic time. Dozens, possibly hundreds, of smaller galaxies, slowly absorbed into one enormous, quiet structure. The measurements that established its record were made in 1990 by Juan Uson, Stephen Bown, and Jeffrey Kuhn, using ground-based telescopes to trace the galaxy's faint outer light far beyond where most surveys had stopped looking. Tracing light that faint is genuinely difficult work. The outer halo of a galaxy like this one is dimmer than the natural glow of Earth's own night sky, dimmer than the scattered light bouncing around inside the telescope's own optics, and separating a real, extremely faint signal from those sources of contamination requires extraordinarily careful calibration, often built up by stacking many individual exposures together and subtracting everything that does not behave the way starlight from a single coherent source should behave. The result held up. IC 1101 has remained, for more than 3 decades, the standard answer to the question of which single galaxy is the largest by stellar extent that we know of. But largest galaxy is not, in fact, a single, settled category, and the record has moved twice more in recent years by a completely different measure. In 2022, A team led by the astronomer Martijn Oe, using the LOFAR radio telescope network spread across Europe, discovered a galaxy named Alcyoneus, after a giant from Greek mythology. Alcyoneus itself, as a stellar body, is an entirely unremarkable elliptical galaxy, about 3 billion light-years away, with a fairly typical mass and a central black hole of around 400 million solar masses. What is not unremarkable is what that black hole has built: two enormous jets of charged particles, launched from opposite sides of the galaxy, terminating in radio-emitting lobes that together span approximately 16 million light-years, more than 150 times the width of the Milky Way. Measured by this radio structure, rather than by visible starlight, Alcyoneus instantly became the largest known structure ever produced by a single galaxy. It did not hold that title for long. In 2024, the same research group, with OE now at Caltech, announced an even larger pair of jets named Porphyrion, after another giant of Greek myth, stretching approximately 23 to 24 million light-years from end to end, the equivalent of roughly 140 Milky Ways laid end to end. The galaxy producing them sits about 7.5 billion light-years away, and the jets themselves date from a period when the universe was less than half its current age, meaning they had to push through a cosmic web that was itself far more tightly packed than the one we see locally today, a detail that genuinely surprised the team that found it. And within roughly a year of that announcement, an even larger structure, designated by its catalogue number rather than a name, was reported with an extent of approximately 26 million light-years, overtaking Porphyrion in turn. There is a deeper reason the diameter of IC 1101 keeps shifting depending on who measures it, and it is the same reason UI Scuti's radius shifted between 2012 and 2023. A galaxy, like a star, does not have an edge. Its bright core fades gradually into a faint stellar halo, which fades gradually into the even fainter intracluster light scattered between galaxies in the same cluster, which fades, eventually, into nothing anyone's instrument can distinguish from the night sky's own background glow. Where you choose to stop calling that light the galaxy is a decision about a brightness threshold, not a discovery about a physical boundary. Set the threshold higher, and the galaxy looks smaller and better defined. Set it lower, and the same galaxy stretches outward by a factor of 10 or more, swallowing every faint stream of cannibalized starlight along the way. IC 1101's two competing diameters, 400,000 light-years against 5.5 million, are not really a disagreement about the galaxy. They are a disagreement about where a fundamentally fuzzy object should be declared to end. IC 1101 is also not alone in its category. It is simply the most extreme known example of a supergiant diffuse galaxy, a class that includes other very large central cluster galaxies such as NGC 6166, sitting at the heart of a smaller and somewhat less extreme cluster. None of these rivals approach IC 1101's scale, but their existence matters for a reason beyond competition. It confirms that what we are looking at is not a singular freak accident, but the predictable outcome of a process galactic cannibalism occurring at the center of any sufficiently rich cluster that will, given enough time, produce something like this wherever the right conditions exist. Abell 2029 happened to have both the richness and the time. Other clusters, slightly younger or slightly less crowded, are presumably still building their own versions of the same thing, on a timescale of billions of years we will never be around to watch finish. So which is the largest known galaxy? It depends entirely on what you choose to measure, and on where you choose to stop counting its faintest light as still belonging to it at all. By visible starlight, the answer is still IC 1101, more or less unchallenged for over 30 years. By radio-emitting structure built from a single galaxy's central black hole, the answer has changed twice in the last several years, and may have changed again since this was written. Neither record is wrong. They are measuring different things, and both keep moving, because we keep building better instruments to look with. Galaxies, on the largest scales, do not behave like islands. They behave like currents. The supercluster that contains the Milky Way is called Laniakea, a Hawaiian word combining lani, meaning heaven or sky, and akea, meaning immense or spacious. immense heaven. The name was proposed by Noah Napoleon, who teaches Hawaiian language at Kapiolani Community College, after the discovery team asked him for something that matched the scale of what they had found. The discovery was announced in September 2014 on the cover of the journal Nature. The lead researcher, R. Brent Tully of the University of Hawaii, had spent decades mapping the large-scale structure of the universe. But the method behind this particular map was different from a simple census of where galaxies sit. It tracked where they are going. Every galaxy's measured velocity is the sum of two things: the steady stretching of space itself, which carries galaxies apart from each other at a rate proportional to their distance, and a smaller, local component caused by the gravitational pull of nearby mass concentrations. Subtract the first component, and what remains is called a peculiar velocity, the genuine, gravity-driven motion of a galaxy, relative to the smooth expansion around it. Tully's team mapped the peculiar velocities of a large number of galaxies across a substantial volume of space, and found that an enormous number of them were flowing in a coherent direction toward a shared destination, rather than moving independently. That shared, coherent flow is what defines a supercluster under this method. Not a fixed boundary you could draw on a map ahead of time, but a basin of attraction, the way a watershed defines the boundary of everything that drains toward the same river, regardless of the terrain in between. The destination all of this is flowing toward is a concentration of mass called the Great Attractor, located in the direction of the constellation Centaurus, approximately 200 million light-years from the Milky Way. It is not a single object. It is a region where the density of galaxies and dark matter is significantly higher than average, exerting enough collective gravity to draw matter toward it across hundreds of millions of light-years. The Milky Way sits well out toward the edge of Laniakea, not anywhere near its center in the suburbs of our own supercluster, gravitationally speaking, slowly drifting toward the Great Attractor, along with everything else nearby. Laniakea itself spans approximately 500 million light-years and contains an estimated 100,000 large galaxies, with a combined mass on the order of 10 to the 17th power times the mass of the Sun 100 million billion solar masses, bound together not by a wall or a filament in the usual sense, but by the simple fact that all of it is falling the same direction. It is worth dwelling on how strange that last sentence actually is, compared to almost every other object we have discussed tonight. A star holds together because gravity pulls its own matter inward against its own outward pressure. A galaxy holds together because stars orbit a shared center of mass. A supercluster, defined the way Tully's team defined it, does not hold together in either of those senses at all. The galaxies inside Laniakea are not orbiting a common center, and they are not bound tightly enough to resist the universe's overall expansion forever. They are simply all moving, for now, in directions that happen to converge on the same distant point, the way 100,000 separate rivers might all happen to drain toward the same lowland basin without any of them being aware the others exist. Eventually, as the universe continues expanding, some of the more distant members of that flow may drift away entirely, pulled instead toward a different, equally temporary destination. Laniakea is real, in the sense that the flow it describes is genuinely happening right now, measured directly in the velocities of real galaxies. It is also, in a way none of the earlier objects in tonight's story quite shared, less a structure than a moment a description of where everything nearby is currently headed, rather than a description of something that will still look the same in another few billion years. In 2023, a more detailed survey using an expanded catalogue of more than 55,000 galaxy distances confirmed Laniakea's size and mapped its boundary with considerably more precision than the original 2014 study allowed. That same survey noted something that should sound familiar by now. The superclusters it mapped, Laniakea included, came out roughly an order of magnitude larger than the theoretical predictions generated by standard cosmological simulations. We will hear a version of this same tension, observed structure outrunning the models built to predict it again before the night is over, and by then it will be considerably harder to explain away. Laniakea, in turn, is not the dominant structure in this part of the universe. It is being pulled, slowly, towards something larger still. The Shapley supercluster, sometimes called the Shapley concentration, is the most massive structure within roughly 1 billion light-years of the Milky Way containing more than 8,000 galaxies, with a combined mass exceeding 10 million billion solar masses, located approximately 650 million light-years away, also in the direction of Centaurus. It carries the name of Harlow Shapley, the American astronomer who first identified the concentration in the 1930s, working at the Harvard College Observatory with photographic plates taken at a modest 24-inch telescope in Bloemfontein, South Africa. By 1932, Shapley had catalogued 76,000 galaxies and noticed something that should not have surprised anyone, but apparently did. They were not spread evenly across the sky. Certain regions, including the direction of Centaurus, showed a conspicuously higher density than everywhere around them. Shapley had no concept of a supercluster to describe what he was seeing. The term simply did not exist yet, but he published the overdensity anyway, and the structure was later named for him once the framework to properly describe it had caught up. A basin of attraction like Laniakea or Shapley is not, strictly speaking, a permanent shape. It is closer to a long exposure photograph of a process still happening, a description of which way everything within a certain volume of space is currently flowing, given the gravitational landscape that exists right now. As the universe continues expanding, and as the relative positions of galaxies continue shifting over billions of years, the exact boundary separating Laniakea's inward flow from a neighboring basin's inward flow will itself drift. Unlike a star or a galaxy, which has, however fuzzy at the edges, an actual physical body holding it together, a supercluster defined this way is held together by nothing but a temporary agreement among billions of galaxies about which direction is inward. That agreement is currently pointing the Milky Way towards Centaurus. There is no law of physics promising it will keep pointing there forever. We can actually measure how fast we are moving along this flow, and the measurement comes from an unexpected source, the cosmic microwave background, the same ancient radiation we will return to later tonight, in a different context. That radiation should look, in principle, almost perfectly uniform in every direction, since it was emitted essentially everywhere in the universe at the same early moment. It does not look perfectly uniform from here. It appears very slightly hotter in one direction of the sky, and very slightly cooler in the opposite direction, a pattern called the CMB dipole, caused by our own motion, the way a sound seems to shift in pitch as you drive toward its source and away from it after passing. From the size of that pattern, astronomers have calculated that the local group is moving at approximately 620 kilometers per second relative to the average rest frame of the universe in the general direction of the constellation Centaurus, very nearly the same direction the Great Attractor and the Shapley supercluster both sit in. We are not simply being told, secondhand, through galaxy surveys, that we are part of a large-scale flow towards Centaurus. The oldest light in the universe shows us the same thing directly, stamped with the Doppler signature of our own motion. The flow does not stop at Laniakea's boundary. The Great Attractor, the gravitational center pulling our own supercluster inward, is itself drifting toward the Shapley supercluster, which sits at the center of an even larger basin of attraction. Everything nearby, our galaxy, our supercluster, the attractor pulling on our supercluster is, in some sense, falling toward the same distant destination, at a pace too slow to ever notice in a human lifetime, but real enough to measure across a few 100 million galaxies. Laniakea was not the first attempt to describe this region of space as a single coherent structure, and it is worth knowing what came before it, because the pattern of revision is the same pattern we have already seen with the largest stars and the largest galaxy. In the 1950s, the French astronomer Gérard de Vaucouleurs proposed what he called the local supercluster, a flattened concentration of galaxies, including the Milky Way, organized loosely around the Virgo cluster. For decades, this was the accepted picture of our place in the large-scale universe. A single supercluster, centered on Virgo, with the Milky Way sitting somewhere along its outer edge. De Vaucouleurs' map was built almost entirely from galaxy positions and brightness, because the velocity data needed to do what Tully's team would later do simply did not exist yet, or could not be measured precisely enough to be useful. It was a reasonable evidence-based picture, built with the tools available at the time, and it was also, in the end, only part of the actual structure. Laniakea did not erase the local supercluster, it absorbed it. the way a more precise map absorbs an older, cruder one. The Virgo-centered structure de Vaucouleurs, identified, turned out to be roughly the inner core of something 4 times larger. Once velocity data revealed the full extent of the flow surrounding it. There is a smaller, closer structure worth mentioning as well, because it sits at a scale between the local group and Laniakea itself, and it shapes the local group's motion in ways that are easy to overlook. In 2014, the astronomer Marshall McCall proposed that the large galaxies surrounding our own local group, including Centaurus A, Messier 81, and several others, spread across roughly a 36 million light-year ring form, a loose, roughly circular arrangement he named the Council of Giants. The galaxies of this council are not gravitationally bound to each other in any tight sense, but their collective arrangement appears to have shaped the orbital motion of the local group within it, nudging our own trajectory long before anyone identified Laniakea, the Great Attractor, or the Shapley supercluster at all. We have, in other words, at least 3 nested descriptions of where we sit and where we are going. A ring of giant neighbors immediately around us, a basin of attraction 500 million light-years across containing all of it, and a still larger structure pulling that basin towards Centaurus, discovered roughly in reverse order of how a person standing on Earth might actually notice them, nearest last. This raises the obvious next question, the one that has been quietly underneath every section so far. If structure keeps nesting inside larger structure star, black hole, nebula, void, galaxy, supercluster, does that nesting ever stop? Is there a scale at which the universe simply runs out of room to organize itself further and becomes, at last, uniformly the same everywhere? According to the cosmological principle, yes. There has to be such a scale, or the entire framework of modern cosmology starts to come apart. What we are about to look at next is the strongest direct test of whether that scale actually exists where the models say it should. Is there a point where gravity can no longer bind a structure into something larger than the rules allow? The honest answer, repeated twice now in the last decade, is that the limit keeps turning out to be larger than whoever calculated it expected. The theoretical ceiling, under the cosmological principle, sits at approximately 1.2 billion light-years. Beyond that scale, in a universe as old as ours, gravity should not have had time to organize matter into anything larger. The number comes from a real calculation, built from the age of the universe and the rate at which structure can grow under standard cosmology. It is not an arbitrary boundary, it is a prediction. That prediction is not purely theoretical paperwork. It has been tested directly using large computer simulations that model the formation of structure across the entire age of the universe, starting from the same tiny density fluctuations Boötes formation depended on and running gravity forward for 13.8 billion years inside a simulated volume. These simulations efforts, with names like the Millennium Simulation, tracking the gravitational evolution of billions of particles standing in for dark matter and galaxies, consistently produce filaments, walls, and voids of a particular characteristic maximum size, closely matching the 1.2 billion light-year figure derived analytically. The Huge-LQG, and everything we are about to discuss for the rest of the night, is not simply violating a back-of-envelope estimate. It is violating the output of some of the most detailed structure formation simulations cosmologists have ever run. The Huge-LQG broke it by more than 3 times over. Large quasar groups, abbreviated LQG, are exactly what the name suggests. Quasars, the brilliant, accreting black holes we spent time with earlier in the night, found clustered together in groups far larger than chance alignment should produce. They are identified using something called a friends of friends algorithm. A quasar is linked to a group if it falls within a set distance of any other quasar already in that group, the way you might trace a social network by connecting anyone who knows anyone already in it. Most such groups are modest, containing 5 to 40 members across 40 to 350 million light-years, sizable by any ordinary standard, but well within what the cosmological principle comfortably permits. They become a genuine scientific problem only at the extreme tail of the distribution, when a single group's membership and size jump far beyond what the rest of the population would predict. In 1991, the astronomer Roger Clowes and his colleague Luis Campusano identified a large quasar group that, at the time, was the biggest known structure in the universe, approximately 2 billion light-years across. It held that record for more than 20 years. Then, on the 11th of January, 2013, Clowes, by then at the University of Central Lancashire, announced something considerably larger. 73 quasars, clustered across a structure with a minimum diameter of approximately 1.4 billion light-years and a maximum extent, along its longest axis, of about 4 billion light-years. They named it, with no attempt at poetry, the Huge Large Quasar Group, the Huge-LQG. It was more than twice the size of the previous record holder, and more than 3 times the theoretical limit the cosmological principle was supposed to enforce. The discovery did not go unchallenged, and the challenge came quickly. Later, in 2013, the cosmologist Tarantula Nebula published an analysis arguing that the statistical significance claimed for the Huge-LQG was substantially overstated, that a structure of comparable size and richness could plausibly arise from pure chance, with no actual physical association between its member quasars at all, simply because of how many possible groupings exist when you are searching a large enough catalogue for the most extreme one. Subsequent papers in the years that followed by other researchers using different statistical methods on the same underlying data produced genuinely mixed results. Some agreed with Nebula, finding the Huge-LQG statistically unremarkable once you account for how the search itself was conducted. Others, using different clustering algorithms on the same quasar catalogue, found independent support for a real physical grouping. As recently as the early 2020s, researchers were still publishing competing analyses of the same 73 quasars, still disagreeing about whether what Clowes found in 2013 was a structure, a statistical illusion, or something in between that neither label quite captures. The Huge-LQG sits at a mean redshift of approximately 1.27, corresponding to a distance of roughly 9 billion light-years, meaning the light defining this entire structure left its source when the universe was less than 5 billion years old, younger than it is now, by more than half. This is worth pausing on, because it is not a story about astronomers being careless. It is a story about how difficult it is to prove that something 9 billion light-years away is actually bound together, rather than simply sitting at similar distances in similar directions by coincidence. Clowes' team used a method that calculates the volume enclosed by the outermost members of a candidate group and compares it against millions of simulated random distributions of the same number of points. Critics argued that method has a tendency to find apparent significance even in genuinely random data if you are specifically searching for the single largest structure in an enormous catalogue rather than evaluating a structure chosen in advance. Both sides have a defensible point. Neither has definitively won. There is a physical reason quasars cluster together in the first place, separate from the statistical argument about whether any one particular cluster is real. A quasar requires 2 things to switch on: a sufficiently massive black hole and a sufficiently large supply of gas falling into it. Both conditions tend to be satisfied more easily in regions of the universe that are already denser than average places, where galaxies are close enough together to merge, funnel gas inward, and trigger exactly the kind of feeding that lights a quasar up in the first place. This means quasars are not expected to be scattered uniformly through space, even under completely ordinary cosmology. They are expected to trace the denser parts of the cosmic web, the way streetlights trace a city's roads rather than its open fields. The genuine scientific question raised by the Huge-LQG is not whether quasars cluster at all, they obviously do, modestly, almost everywhere, but whether this particular clustering, at this particular size, is larger than even that ordinary tendency would predict. That is a much narrower and much harder question to answer than it first appears, and it is the question that Nebula, Clowes, and everyone who has published on this structure since have actually been arguing about. The Huge-LQG was not the first claimed structure of this kind to face this exact argument, and it would not be the last. And it was not even the first structure to claim the title of largest in the universe under the name Great Wall. That distinction belongs to an earlier discovery entirely. In 1989, the astronomers Margaret Geller and John Hucre, mapping galaxy redshifts from the Harvard-Smithsonian Center for Astrophysics, identified a sheet-like concentration of galaxies stretching across approximately 500 million light-years, small by tonight's standards. But, at the time, the largest structure ever directly mapped, and the discovery that first popularized the term Great Wall for this kind of object at all. It was, for over a decade, simply called the Great Wall, before later and larger discoveries forced everyone to start attaching qualifying names to keep the growing list straight. A separate, later structure, the Sloan Great Wall, identified in 2003 by a team led by Richard Gott, spans approximately 1.4 billion light-years, a wall of galaxies rather than quasars, discovered through an entirely different survey, and it sits comfortably within the cosmological principle's theoretical limit. It is enormous by any ordinary measure, and entirely unremarkable by this particular one. The pattern across all of these discoveries is the same: the larger and more extreme a claimed structure, the harder it becomes to distinguish a genuine gravitationally bound object from an extreme but coincidental clustering of unrelated things, and the more carefully the claim has to be tested before it can be trusted. What is not seriously disputed is that something occupies that region of sky at a similar distance, in genuinely unusual concentration. What remains disputed is what to call it, and whether the rules that built our model of the universe need to bend to accommodate it, or whether the rules are fine and the apparent structure is simply an artifact of how we searched for it. Both possibilities remain open more than a decade after the original announcement. It is worth saying plainly what is and is not at stake in a dispute like this one, because from a distance it can sound like astronomers arguing over a technicality. It is not a technicality. The cosmological principle is the single assumption that makes it possible to write down a set of equations describing the entire universe at once, rather than having to model every region of space individually on its own terms. If structures genuinely exist that violate it at the scales the Huge-LQG, and the structures we are about to discuss claim to occupy, then the equations cosmologists currently use to describe the universe's overall geometry and expansion are not simply slightly inaccurate, they are missing something structural. That is the size of the claim hiding underneath a debate that, on the page, looks like a disagreement about how to count quasars. This is also why the burden of proof sits so firmly on the side of anyone claiming a record-breaking structure, rather than on the side of the existing model. Lambda CDM has survived an enormous range of independent tests: the cosmic microwave background, the abundance of light elements forged shortly after the Big Bang, the large-scale distribution of ordinary galaxies, the expansion history measured through distant supernovae, and passed nearly all of them with remarkable precision. A single contested quasar group does not get to overturn that body of evidence by itself, no matter how striking it looks on a map, and neither, on its own, does a single contested arrangement of gamma-ray bursts. What either one can do, if it survives every attempt to explain it away, is force a revision at the edges of the model rather than its center. That is a much smaller claim than cosmology is wrong, and it is also the only claim any of tonight's contested structures are actually in a position to make. Roger Clowes' own students have continued this exact line of inquiry. In 2021, Alexia Lopez, a doctoral student working under Clowes at the University of Central Lancashire, reported a structure she named the Giant Arc, a curved arrangement of galaxies, galaxy clusters, and intervening gas, spanning approximately 3.3 billion light-years, found using a method entirely different from either galaxy redshift surveys or quasar clustering. Lopez traced the structure using absorption lines imprinted on the light of background quasars by diffuse magnesium gas sitting between those quasars and Earth, using the quasars not as the objects of interest themselves, but as distant lamps, shining through foreground material too faint to detect any other way. The same way you might infer the shape of fog by watching how it dims a row of distant streetlights. In 2024, using the same method, she reported a second structure nearby in the sky, and at the same enormous distance, a ring-shaped arrangement, nicknamed the Big Ring, with a diameter of approximately 1.3 billion light-years and a circumference of roughly 4 billion light-years, sitting only 12 degrees away from the giant arc on the sky, at essentially the same cosmic distance and the same cosmic time. Both structures, like the Huge-LQG and the Great Wall before them, exceed the cosmological principle's theoretical limit. Lopez's own statistical analysis of the Big Ring put its significance above the 5 sigma threshold scientists conventionally require before calling a result a confirmed discovery, rather than a statistical fluctuation, a notably higher bar than either the original Huge-LQG or Great Wall announcements were able to clear at the time. 2 structures, found by 2 completely different methods, sitting unexpectedly close to each other in both space and time, neither one easily explained by the same standard model that the Huge-LQG and the Great Wall were already straining against. The question this section opened with has not gotten any closer to a single answer. It has simply gathered more company. We are about to look at a second structure that raises the exact same question at an even larger scale, with even less certainty about the answer, and this time, the data behind it comes from an entirely different kind of light. The largest claimed structure in the observable universe was not found by looking at galaxies at all. It was found by looking at the most violent flashes of light the universe produces, and noticing that too many of them were clustered in one direction. Gamma-ray bursts are brief, extraordinarily energetic flashes of high-energy radiation, generally produced by the catastrophic collapse of a massive star or the merger of 2 neutron stars. A single burst can release more energy in a few seconds than the Sun will produce across its entire 10 billion-year lifetime. They are also, conveniently for cosmology, visible across enormous distances, which makes them useful as distance markers in regions of the universe too faint and too far away to map any other way. There are, broadly, 2 kinds. Long gamma-ray bursts, lasting anywhere from roughly 2 seconds to several minutes, are thought to come from the core collapse of an unusually massive, rapidly rotating star, a death violent enough to launch narrow, relativistic jets of particles straight through the collapsing star itself, visible from enormous distances if one of those jets happens to point toward Earth. Short gamma-ray bursts, lasting less than 2 seconds, are linked instead to the merger of 2 neutron stars, or a neutron star, and a black hole, a different kind of catastrophe entirely, confirmed directly in 2017, when a gravitational wave detection of exactly such a merger was followed, a little over a second later, by a short gamma-ray burst detected from the same patch of sky, definitively linking the 2 phenomena for the first time. Most of the 14 bursts that define the Hercules-Corona Borealis Great Wall are of the long variety, distant, dying, massive stars, collapsing one after another, across an enormous span of cosmic time and cosmic distance, their deaths arriving at our detectors decades apart, even though the stars themselves may have died at very nearly the same cosmic moment. Between 1997 and 2012, 2 space-based observatories, the Swift satellite and the Fermi Gamma-ray Space Telescope, recorded the positions and distances of hundreds of these bursts across the sky. A team of American and Hungarian astronomers, led by István Horváth, John Hakila, and Zsolt Bagoli, sat down with 15 years of that accumulated data and noticed something that should not have been there: 14 gamma-ray bursts, clustered together in the same region of sky, at very nearly the same redshift, meaning very nearly the same distance from us. The clustering was tight enough, and the probability of it occurring purely by chance low enough, that the team concluded they were looking at a single physical structure, rather than 14 unrelated events that happened to align. They announced the discovery in November of 2013 and published the full statistical analysis the following year. The structure they had found stretched across approximately 10 billion light-years by a wide margin, the largest claimed structure anyone had reported. Here is a detail about the discovery that the original team did not plan and did not particularly want. Horváth and his colleagues never gave the structure a name. They were, by Hakila's own later account, considerably more concerned with whether the clustering was statistically real than with what to call it. The name Hercules-Corona Borealis Great Wall, describing its position near the border of those 2 constellations, was coined a few weeks later by a teenager in the Philippines, reading a science news report about the discovery and editing the structure's description on a public encyclopedia. The name spread through later articles and television segments faster than any of the original researchers expected, and within a couple of years, Hakila himself had simply started using it too. The largest named structure in the observable universe, as far as we know, was named by someone who had nothing to do with discovering it. The numbers themselves are worth holding clearly, because every comparison in tonight's story has been building toward them. The Great Wall's longest dimension runs to approximately 10 billion light-years. Its width, across the second axis, is approximately 7.2 billion light-years. Its thickness, the shortest dimension, is approximately 1 billion light-years. The observable universe, in total, is approximately 93 billion light-years across. The Great Wall, by its longest measurement, occupies more than 10% of that entire diameter, a single structure spanning a tenth of everything we can, in principle, ever see. The method itself is worth knowing, because it explains why this particular structure took so long to notice. Horvath and his colleagues did not simply scan the sky for clusters by eye. They divided the entire celestial sphere into 9 roughly equal regions and compared the distribution of gamma-ray bursts across all 9, looking for any single region with a statistically unlikely excess. One region stood out, centered near the border of Hercules-Corona Borealis, with its 14 defining bursts falling within a redshift range of roughly 1.6 to 2.1, close enough together, in cosmological terms, to plausibly belong to the same structure, rather than being scattered across a meaningfully different range of distances and simply appearing close together by chance projection on the sky. Its total mass is estimated at roughly 5 quintillion times the mass of the Sun 5, followed by 18 zeros, or, expressed differently, somewhere in the neighborhood of 100,000 galaxies worth of material gathered into one elongated structure of galaxies, quasars, and dark matter. The theoretical limit, imposed by the cosmological principle, as we established earlier tonight, sits at approximately 1.2 billion light-years. The Great Wall, at its longest extent, is roughly 8 times that limit. It is not a modest violation of the rule. It is the largest violation anyone has reported. Set against everything else covered tonight, the scale finally becomes almost impossible to misplace. Stevenson 2-18, the largest star we measured, was 3 billion kilometers across. The Great Wall is roughly 30,000 billion times that distance. Laniakea, the supercluster containing our entire galaxy, spans 500 million light-years. The Great Wall is 20 times longer than the structure that contains the Milky Way itself. Every object we have spent the night with, the star, the black hole, the nursery, the void, the galaxy, the supercluster, the disputed quasar group, would fit inside the Great Wall's longest dimension, with room left over for several more of each. And here is where the honesty has to be as careful as the enthusiasm. Horvath, Hackula, and Begley themselves described the Great Wall as a putative structure, putative meaning supposed, assumed for the sake of discussion, not yet confirmed. That word is doing real work. It means the discoverers themselves are not claiming certainty. The sample of 14 gamma-ray bursts is small, the sky is large. Clustering this tight, in a small sample, is statistically unlikely to occur by pure chance, but unlikely is not the same as impossible, and a structure built from just 14 data points carries more uncertainty than one built from thousands of galaxies with directly measured redshifts, the way IC 1101 or the Boötes Void were measured. Independent confirmation, using a different and larger dataset, has not yet definitively settled the question one way or the other. Some researchers analyzing the same gamma-ray burst catalogs since 2013 have found supporting evidence for genuine clustering beyond what chance would produce. Others have raised the same kind of statistical objections that were raised against the Huge-LQG, that searching an entire sky survey for its single most extreme outlier will tend to manufacture apparent significance, even from data with no underlying physical structure at all. So we are left, at the very largest scale anyone has ever measured, with the same open question that has followed us through every section of tonight's story, just stated at maximum volume. If the Great Wall is real, the cosmological principle, the founding assumption that the universe looks roughly the same everywhere once you zoom out far enough, is wrong, or at minimum needs to be revised to allow for occasional structures far larger than it currently permits. If the Great Wall is not real, if it is, instead, a chance alignment of 14 otherwise unrelated bursts, amplified by the fact that astronomers were specifically searching for the largest possible structure in their data, then the cosmological principle survives intact, and the Huge-LQG and the Great Wall both join a list of claimed record holders that did not, in the end, hold up. A follow-up study published in 2015, with Horvath and Bagoli joined by additional collaborators, returned to the gamma-ray burst catalogue with several more years of accumulated data and reported that the new bursts continued to support the original clustering rather than diluting it the way you would expect if the first result had simply been a fluke produced by a small, unlucky sample. That is meaningful evidence in the Great Wall's favour. It is not, on its own, the kind of independent confirmation using an entirely different tracer of large-scale structure, the way gravitational lensing independently confirmed what rotation curves had already suggested about dark matter, that would settle the question outright. Gamma-ray bursts remain rare events. Even with additional years of data, the sample defining this structure is still measured in the dozens, not the thousands. We do not know which of those two outcomes is correct. Neither does anyone else, as of this recording. Think back to where tonight began moving at the speed of light, 10 billion years of travel behind you, watching 14 flashes of ancient light resolve into the outline of something too large for the rulebook. That outline has not changed in the time it took to get here. What has changed is how much weight you now know that single image is actually carrying. A structure that might be the largest thing ever measured, or might be nothing more than an extremely unlucky or extremely interesting coincidence, sitting at the exact edge of what 14 data points can responsibly tell us. There are real reasons to think the question will not stay open forever. The Vera C. Rubin Observatory in Chile, named for the same astronomer whose rotation curve measurements first forced dark matter into the mainstream of physics, began its main 10-year survey of the southern sky recently, and is expected to catalogue a far larger number of distant galaxies, and indirectly a far larger sample of background quasars useful for tracing structures like the Giant Arc and the Big Ring than any previous survey. Future gamma-ray missions, designed with greater sensitivity than Swift or Fermi, should eventually accumulate a GRB catalogue large enough to test the Great Wall's clustering with the kind of statistical confidence 14 bursts alone can never provide. None of this guarantees an answer arrives soon. It does mean the open question we are leaving tonight's story with is not stuck in place by a lack of effort. It is stuck in place by a lack of data that better instruments, already being built or already running, are actively working to provide. Science does not require that question to be answered to be worth taking seriously. It only requires that the question stay open until the evidence is strong enough to close it. This one is still open. It may stay open for years. That is not a weakness in the story. It is the most honest place the story could possibly end. There is one more structure left to talk about tonight, and it is the strangest one, because you cannot see it, and you are inside it right now. 85% of the matter in the universe is invisible, not hidden behind something, not too faint to detect with a better telescope, invisible in the literal sense. It does not emit light, does not absorb light, does not interact with light at all. We call it dark matter, and despite the name being almost a century old, we still do not know what it actually is. The first hint that it existed came in 1933 from the Swiss-American astronomer Fritz Zwicky, studying the Coma cluster, a collection of more than 1,000 galaxies roughly 300 million light-years away. Zwicky measured how fast individual galaxies within the cluster were moving relative to one another, using a tool called the virial theorem to estimate how much total mass would be needed to gravitationally hold a cluster moving that quickly together, rather than flying apart. He then separately estimated the cluster's mass from its total visible light, assuming its stars had a typical mass-to-light ratio. The two numbers did not match, not by a small margin. The mass needed to explain the galaxy's velocities was roughly 10 times larger than the mass visible in starlight. Zwicky concluded that the cluster must be full of what he called, in German, dunkel Materie, dark matter vastly outweighing everything we could actually see. He was right, in substance, decades ahead of anyone else. He was also almost entirely ignored. The astronomical community of the 1930s had no framework for taking the claim seriously, and the idea sat largely dormant for nearly 40 years. It resurfaced because of a problem nobody was specifically looking for. In 1968, Vera Rubin, working with the instrument builder Kent Ford at the Carnegie Institution of Washington, pointed a newly improved spectrograph at the Andromeda Galaxy to measure how fast stars orbit at different distances from its center what astronomers call a rotation curve. The expectation, based on ordinary Newtonian gravity and the visible distribution of mass in the galaxy, was straightforward. Stars near the bright, mass-dense center should orbit quickly, and stars further out, where there is visibly less material, should orbit more slowly, the same way Pluto moves more slowly around the Sun than Mercury does. By the end of their very first night of observing, Rubin and Ford had a rotation curve that did not look like that at all. The stars far from Andromeda's center were moving just as fast as the stars near it. The curve was flat, not falling. Rubin and Ford published the initial Andromeda data in 1970, and over the following decade extended the same measurement to dozens of other spiral galaxies. The flat curve was not a quirk of one unusual galaxy. It was, apparently, how every spiral galaxy behaved. There were only two ways to explain what they had found. Either the law of gravity itself needed to be rewritten at galactic distances, or every one of these galaxies was embedded in a much larger halo of unseen mass that did not concentrate at the center the way visible stars do, but spread outward through and beyond the visible disk, providing exactly the additional gravitational pull needed to keep those outer stars from flying off into space. Rubin favored the second explanation, and by the early 1980s, with rotation curve data accumulating from galaxy after galaxy, so did most of the field. Zwicky's 1933 claim, dismissed for 4 decades, had effectively been independently rediscovered, this time with enough supporting evidence that it could no longer be set aside. Since then, the evidence has only widened, and it no longer rests on rotation curves alone. Massive galaxy clusters bend the path of light passing near them, an effect called gravitational lensing, predicted by general relativity. The amount of bending observed around many clusters is far greater than the visible mass in those clusters could produce on its own, but it matches almost perfectly once you add in the same invisible mass that rotation curves require. The clearest single image of this comes from a system formerly catalogued as 1E0657-56, and known to almost everyone else as the Bullet Cluster. 2 galaxy clusters, roughly 3.7 billion light-years away, caught in the act of colliding, having smashed through each other at several thousand kilometers per second sometime in the last 100 million years or so. Observations made in 2006 combined 2 completely different kinds of data over the same patch of sky. X-ray images, taken with the Chandra X-ray Observatory, show the colliding cluster's visible gas, by far the largest source of ordinary, light-emitting matter, in each cluster having slammed together, slowed, and heated into a glowing, bullet-shaped cloud near the center of the collision, the way 2 clouds of smoke might tangle and compress on impact. Separately, gravitational lensing maps, built by measuring how the light of more distant background galaxies is subtly distorted as it passes through the cluster, reveal where the actual bulk of each cluster's mass is sitting. The 2 maps do not agree. The lensing mass sits well ahead of the X-ray gas, tracking the individual galaxies of each cluster, which pass through each other largely undisturbed, rather than the slowed, heated gas trailing behind them. Whatever makes up most of the mass in those clusters did not slow down in the collision the way the gas did. It does not interact with itself, or with ordinary matter, the way gas does. It passed straight through, as if the rest of the collision were not even there, and the only thing that gave its position away was the gravity it could not help exerting. The third major line of evidence comes from the cosmic microwave background, the faint, ancient radiation left over from when the universe was only about 380,000 years old, mapped in extraordinary detail by the Planck satellite earlier this century. The precise pattern of tiny temperature variations across that radiation depends sensitively on exactly how much ordinary matter and how much dark matter existed at that very early moment, because the two interact with light differently and therefore leave different fingerprints. The pattern Planck actually measured fits a universe composed of roughly 5% ordinary matter, roughly 27% dark matter, and the remainder the majority of everything, an even stranger component, called dark energy, responsible for the universe's accelerating expansion, which is a separate mystery for a separate night. 3 independent lines of evidence, the motion of galaxies, the bending of light, and the structure of the oldest light in the universe, all point to the same invisible mass, in roughly the same proportions, despite measuring completely different things in completely different ways. That convergence is what makes dark matter difficult to dismiss as a measurement error or a flaw in one particular method. It would have to be the same coincidental error occurring independently in three unrelated kinds of observation, which is its own kind of improbability. It would be dishonest to claim every astronomer agrees that dark matter is, in fact, made of particles at all. A minority position, called modified Newtonian dynamics, proposed by the physicist Mordechai Milgrom in 1983, suggests instead that the law of gravity itself behaves slightly differently at the extremely weak accelerations found at a galaxy's outer edge, and, strangely enough, this approach works reasonably well at predicting flat rotation curves in individual galaxies without requiring any unseen matter at all. Where modified gravity struggles is at the scale of galaxy clusters, and the bullet cluster specifically, where the separation between visible gas and the inferred mass is much harder to explain through a gravity tweak alone. Most working cosmologists consider the particle explanation considerably better supported across the full range of evidence, but the alternative has not been definitively ruled out, and a small number of serious researchers continue to develop it. Science rarely closes a door this firmly while leaving it completely unlocked. This is one of the places it has, and yet, after nearly a century of confirming that dark matter exists in ever more precise and varied ways, we still do not know what it is made of. The leading theoretical candidates are particles that interact with ordinary matter only through gravity, and possibly one other extremely weak force, broad categories with names like WIMPs, weakly interacting massive particles, and axions, far lighter hypothetical particles originally proposed to solve an entirely different problem in particle physics. Dedicated detectors, buried deep underground to shield them from ordinary cosmic ray interference, have spent decades waiting for one of these particles to collide, just once, with an ordinary atomic nucleus. Experiments with names like Lux Zeppelin, sitting nearly a mile beneath the Black Hills of South Dakota in a converted gold mine, and the Xenon series of detectors, housed beneath a mountain in central Italy, use enormous tanks of ultra-pure liquid xenon watched over by extremely sensitive light sensors, waiting for the faint flash that a single dark matter particle striking a single xenon nucleus would theoretically produce. Other experiments search a completely different way, looking for axions by attempting to convert them into ordinary photons inside powerful magnetic fields. None of these experiments run continuously for years at a time, in some of the quietest and most carefully shielded environments human beings have ever built, has yet produced a confirmed detection. Each new null result narrows the range of properties dark matter is allowed to have, without ever telling us what it actually is. We have weighed dark matter. We have mapped where it sits, galaxy by galaxy, cluster by cluster, across the entire observable universe. We have never once directly caught a piece of it. There is a second invisible component sitting alongside dark matter in that Planck satellite breakdown we mentioned a moment ago, and it deserves at least a brief acknowledgement, even though it belongs to a different night's story. Dark energy, the term given to whatever is causing the universe's expansion to accelerate rather than slow down under its own gravity, the way a simpler universe would, makes up the remaining roughly 68% of everything, dwarfing both ordinary matter and dark matter combined. We understand dark matter's behavior, even without knowing its composition, well enough to map it with real confidence. Dark energy resists even that. We can measure its effect on the universe's expansion with considerable precision. We have, essentially, no working theory for what it physically is. Tonight's story will not attempt to resolve that one. It is enough, for now, to know it is there, sitting underneath everything else we have discussed, quietly outweighing all of it. It is passing through you right now. Through this room, through the walls, through the planet beneath the building you are in, without slowing down and without leaving any evidence that it passed at all. The particles responsible for holding entire galaxies together, including the one you live in, are moving through your body at this exact moment, and neither of you will ever notice the other. The Milky Way itself sits inside its own halo of this material, and the halo is considerably larger than the visible galaxy it surrounds. The bright disk of stars we usually picture when we picture our own galaxy is approximately 100,000 light-years across. Current estimates of the Milky Way's dark matter halo put its extent at several 100,000 light-years, possibly farther, an invisible sphere of mass, several times wider than every star we can see, holding the visible galaxy together from the outside in, the same way an invisible halo holds together every other spiral galaxy whose rotation curve Vera Rubin and Kent Ford ever measured. You are not just standing on a planet, orbiting a star inside a galaxy. You are standing somewhere near the middle of an invisible sphere of matter several times larger than the entire visible Milky Way, and until the 1970s, nobody studying this galaxy had any reason to suspect it was there at all. That is where tonight's hierarchy actually ends, not with the largest structure, but with the most common substance, sitting quietly inside every structure we have spent the last several hours measuring. The stars, the black holes, the nebula, the void, the galaxy, the superclusters, the contested quasar group, the still uncertain wall stretching across a tenth of the visible universe. Every one of them is embedded in a scaffolding of matter we cannot see, did not predict in advance, and still cannot identify. We found dark matter by noticing that the universe did not behave the way visible matter alone would require. We are finding the Great Wall and the Huge-LQG before it, the same way by noticing that the universe does not always behave the way our models require, and choosing to trust the observation over the model until something forces us to decide otherwise. Zwicky made this same observation in 1933 and was ignored for 40 years. Rubin and Ford made it again in 1968 and were eventually believed. Horvath, Hackler, and Bergoli made a version of it in 2013, and the field is still deciding. The pattern connecting all three is not a story about astronomers being slow to catch on. It is a story about how much evidence it actually takes before a genuine anomaly is allowed to change a settled model, and how that amount of evidence is not the same for every claim. A sugar cube of dark matter eventually convinced an entire field, while 14 gamma-ray bursts have so far convinced roughly half of it. Let us go back, for a moment, to where tonight began. You were moving at the speed of light, 10 billion years of travel behind you, watching 14 points of ancient light resolve into the outline of something the textbooks said could not exist. That image has not gone anywhere. It is still out there, exactly as old, exactly as uncertain as it was 3 hours ago. What has changed is everything you now know sits underneath it, the dying stars, the black hole too massive for its own equations, the nursery still arguing with itself about how big a star is allowed to be, the void empty enough to have hidden the rest of the universe from anyone living inside it, the galaxy that may or may not still hold the record for its own size, the supercluster slowly falling towards something larger. The quasar group, nobody can quite agree, is real. And now, underneath every single one of those things, an invisible substance that built the scaffolding for all of it before a single star had formed. None of that resolves the question the Great Wall raises. It was never going to. What it does is place that one open question inside a much longer pattern, a universe that keeps turning out to be stranger, larger, and less settled than whatever model we were using to describe it the year before. That pattern does not require an answer tonight. It has been running for nearly a century, and it will likely still be running long after this particular question is settled, replaced by some new structure that breaks some new theoretical ceiling, measured by some new instrument that does not exist yet. The dark matter moving through this room right now does not know any of this. It does not know what a model is, or what a limit is supposed to be, or what year it currently is, or that anyone is listening. It is simply here, holding the galaxy together, the way it has for longer than the sun has existed, asking nothing of you in return. Somewhere above the roof of wherever you are listening from, the same sky that contained 14 gamma-ray bursts, a void with 60 lonely galaxies, and a star 3 billion kilometers across is still there, turning slowly overhead the way it has every night of your life, whether or not you ever look up to check. None of it is waiting for you specifically. All of it is, in some sense, still there for you anyway. The universe outside is 13.8 billion years old. The Hercules-Corona Borealis Great Wall, real or not yet confirmed, sits roughly 10 billion light-years away, in a part of the sky most people will never think to look toward. And somewhere between those two facts, in this room, at this hour, you are the only part of any of it that is awake enough right now to notice. Good night.